How can a wormhole grow faster than the speed of light?
Well, locally, each piece of it is growing. The rule is not that one thing can't exceed the speed of light. It's one thing cannot pass another close by at faster than the speed of light. The universe, for example, in some sense grows faster than the speed of light. The accelerated expansion of the universe tells you that if you're far enough away, just the Hubble law, that things will be moving away from you faster than the speed of light. But it does tell you that you can't get information from that far away. And that's what creates a horizon. It creates a cosmic horizon. The same is true here. The wormhole can grow, but if it's growing that fast, you can't get through it, for one thing, and you can't receive signals from far away along the wormhole unless this idea of classical information being sent back and forth can come and slow the growth of the wormhole. And that is something that there's mathematics for it. And in some way, it's being tested in the laboratory, not on real wormholes, but in entangled quantum computers.
So if the information in everything is really all scrambled up and delocalized, why does it act in any way that makes sense to us? Like, why is physics local to us?
That is a really good question. Now, if you just take some random quantum system, it will have some features that look somewhat gravitational in character, but it will not have the degree of locality that we expect in the real world. It's only very, very special quantum systems, very, very special candidates for the holographic screen, let's say, which show the kind of locality which you're asking about. Those special quantum systems are generally gauge theories, whatever. If you don't know what that means, that's okay. And they're also very, very strongly coupled, very difficult systems to analyze. So you're pointing at one of the most important questions to understand what the nature of the very, very special systems that behave with this kind of ultra locality that the real world seems to have. And that's as far as I can go with it, because I think the answers are yet to be given.
Can you say a few more words about the growth of quantum complexity and how it corresponds to the non-traversability of wormholes?
So many words you wouldn't believe it. And I have. But I'm not sure this is the venue for it. Quantum complexity, well, I'll tell you what quantum complexity is. First of all, let me tell you what complexity is. Complexity means lots of different things to different people. You might think, for example, a beautifully designed building or something, or a beautifully designed car is complex. No, it's less complex than almost anything you can think about in that sense. Complexity is used in other words. I have a very complex relation with my mother-in-law. Unfortunately, fortunately, I had a very good relation with my mother-in-law, but you could use the term that way. In fact, a very special thing is meant. Complexity, if you have a given problem, complexity is a measure of the shortest number of steps to solve that problem. Let me give you an example. Theorem proving. You start with a bunch of axioms, and now you have some theorem that you think might be a theorem. And so you go to try to prove it, and you prove it. Okay, it took you a certain number of steps. That number of steps might not be the cheapest and least number of steps that it takes you to prove the theorem. What do I mean by steps? Steps are the use of the logical axioms together with the rules of logic, each one being used once as a step. Your proof might involve 550 steps. The complexity of a theorem is a measure of the least possible number of steps that it would have taken to prove the theorem. Another example from quantum mechanics or quantum computation is you have a quantum computer and you're going to put into it some simple state, and you want to run that computer and get to another state which may have some interesting information in it. Okay, quantum state of a bunch of qubits or something like that. You can think of different ways of getting there. There are different routes, different series of gates, different series of processes that could bring you to that target state. The complexity of the state is a measure of the fewest number of simple operations that can get you there. That's the notion of complexity. Now, that's exactly the notion that's used in this wormhole situation. The wormhole grows, which is simply another way of, which means that the quantum state of the two black holes evolves with time. It's a general feature that complexity increases with time. In other words, you go to states which are harder and harder to get to, which would take more and more steps to get to them. And curiously, interestingly, there appears to be a connection between how complex the quantum state of the black holes is and how big the wormhole is. That seems to be something that's fairly well confirmed by now. And so it is believed that the growth of the interior of the wormhole is equivalent, that's the gravitational side, that's the general relativity side, equal to the tendency for quantum complexity to increase with time for a chaotic quantum system.
So I was wondering, since you said that the center of a black hole, or at least the holographic surface of the center of a black hole, acts like a fluid, would solving
the horizon, which is a kind of holographic surface, yes.
Okay, so if it acts like a fluid, would solving the Navier-Stokes equation be a step forward to figuring out what happens at the center of a black hole?
I rather think, frankly, I think it will happen the other way. That people will be able to solve the gravitational equations for this fluid and make steps that direct attack on the Navier-Stokes equations would be too hard for. So my guess is it will happen the other way, that not solving the Navier-Stokes equation won't teach you that much about black holes, because I think it's just too hard to do, but solving black hole equations, which are a lot easier because they're just Einstein's equations, might very well teach us a lot about dynamics of fluids. That would be my best guess as to which way the information will flow there.
I was wondering if, so you mentioned there is a bound on the viscosity of the black hole and the entropy. So since the viscosity somehow seems to be on the surface of the black hole, is there a relationship between the surface of the black hole and the entropy? And if so, why?
Black holes and horizons have entropy. They have a uniform entropy distributed over the horizon. They also have viscosity. So it was realized by, I think he was a condensed matter physicist, Son, S-O-N, that no matter what he tried to do to the black hole, he could never get the viscosity of the surface fluid to be less than a certain amount, which was proportional to the entropy. That was a pure black hole study. And it turned out that when people looked at experiments on the least viscous fluids, no matter how they manipulated the fluids experimentally, nobody found a fluid that exceeded the bound. It was Son and Staronets who discovered this bound. I just took that as an example. There's nothing particularly special. There are lots and lots of examples like this. This one was easy to explain. There's a nice simple equation that goes with it, and it's so down to earth that it's very easy to understand, not understand where it comes from, why it's true, but what it says.
I have two questions. The first one is, I'm not very familiar with this quantum gravity before this lecture. And there's one thing that seems very weird to me is that where is the quantum holograph? And does it physically exist? And this is
You're asking where the quantum...
Yeah.
I think the answer is that you take any region, whatever, this region here of space, and you want to, the room, and you want to ask how the information is encoded, And the answer is that the amount of information you need to describe the interior of this room is never more than the surface area of the boundary of the room. And so you can always say, you pick your region, and then the answer will be on the boundary of that region. So it's a mathematical statement. What about the universe? Well, the universe does have a horizon. The natural place for the hologram describing the entire universe would be at the horizon of at the cosmic horizon of the universe. But that's something that is still being studied. So the natural thing to say is we take the whole entire observable universe. It's bounded by something called the cosmic horizon, and that would be the natural place where you might want to say the hologram was. Now, I'm not sure that all my colleagues agree with that, and that's still something that I think is work in progress.
Famous quote-unquote historical dilemma is that the Copenhagen interpretation of quantum mechanics is not reversible, while the Schrodinger equation is very much time symmetric. Do you believe that these deeper insights into the workings of quantum mechanics and as they relate to general relativity, as you laid out in the lecture, will deepen our understanding of our interpretation of the wave function, or even perhaps change or offer a new interpretation of the wave function?
I'm only going to say that that's a wonderful question. I think that is a really, really good question. I've always felt that the puzzles of quantum mechanics, the many worlds interpretation, all the very, very confusing things about quantum mechanics would only eventually get solved when we understand the connection with gravity. I still think that, but if I knew how to do it, how to make those connections, I would have published them. My feeling is that the answer to your question is understanding these aspects of quantum gravity will tell you more about the inner workings of quantum mechanics, but nobody has really, that's not been a primary concern of the people doing this kind of work. They tend to be very focused, pragmatic people, if you can call a theoretical physicist pragmatic, who will tend to solve problems that can be solved. This is part of the art of being a good theoretical physicist, is to identify those problems which are hard enough that the results of a solution, will matter and be important, but were not so hard that we'll just sit around for 100 years scratching our butts over them. And so the general feeling of my friends and so forth, and I sort of share it, is that these problems of the foundations of quantum mechanics are real problems, but boy, they've been around a long time. People have struggled with them. People have not been able to make any real sense out of it. It's not even clear they're real. What Feynman said about it, he said the problems are so confusing that he can't even tell if there's a real problem. And that is the way it feels. It's like thinking about consciousness so the pragmatic side of physicists tends to make them steer away from problems like that. Will they come back to it? Perhaps. But at the present time, I think all of this has not impacted the most fundamental understanding of quantum mechanics, which is disappointing in a way.